look up like what a cinch is? How do you not know what a hyperbolic sine is?
I mean, we never teach hyperbolic sines or cosines, right? So like they've cut that out completely.
I picked it up, and I'm not.
I mean, all you have to do is just look it up, right? It's also like take your definition of sine and take the i's out, right? That's the. It's,
Right?
all right. I guess I should start. Okay, so for those of you that for those of you that have contacted me specifically about codes, just chill. I'm gonna send an email when I get home tonight. Okay, those of you that talked to me after class last time, just wait. It'll be coming tonight. This is the second homework assignment. It looks like a lot of questions, but a lot of these are pretty easy. One thing we're gonna do today is talk about polar representation of complex numbers, and so a lot of this stuff is just calculating polar representations and angles. The proofy questions this time, there's only a couple of them, but then there's these awesome ones down at the bottom. You don't need to do this, but I have a lot of ongoing sort of undergraduate research questions that focus around the ideas that show up in 75 to 77, which is about feeding complex functions into themselves and then studying the behavior of what that looks like. So if you've ever seen pretty pictures of the Mandelbrot set or the Julia set, these questions introduce those ideas. So I have a whole program I did for the Frost a couple years ago that was about doing this, but with matrices instead of complex numbers. Right. So these are fun questions, and especially if you like the blend of computing with mathematics, there's like a lot of really interesting things to do here. Anyway, so you got nothing else to do. You want to sit around and do some math questions, and you feel free to do those. Yep. All this is you don't need to. This is optional, for sure. Yeah, anything proof-based is optional, and certainly if I think something is awesome, it means it goes way beyond the scope of like me showing you what the polar decomposition of complex number is. In which case, it doesn't really seem fair to require that you do that on top of your algebra sequence and your discrete sequence and your analysis sequence and everything else. So, who's teaching 412 this year? Cool. All right, maybe I'll teach it next year. I think it's my turn. I could request it. To have couple some complex analysis, some real analysis. All right, so last time we talked about, I haven't graded your quiz yet, so I'll get to it. My daughter got sick over the weekend. Okay, so what did we talk about last time? Like, what's the upshot? I know last time was really theoretical, right? Like, we did a lot of theory last time. What's the upshot of what we did last time? Like, the takeaway message of what we did. Yeah, plugins, that's actually, if you want like a boiled down digest of what we did is, just plug in Z. Okay, so when we say just plug in Z, the name of the theorem we're referring to is the extension theorem, right? So the extension theorem said that basically, if this converges as a real power series, x minus, let's call this Cn, not to be confused. Why am I writing so fast? I'm like all frantic. Just came out of calculus. Or people don't remember things like how to integrate 1 over x cubed. Okay. If this, you guys remember how to integrate 1 over x cubed, right? All right. If this converges as a real power series, on the set x minus a is less than r, it also converges as a complex power series with the same estimate. It also converges as the sum of Cn c minus a to the n on z minus a less than r, same set. Now, you might notice that there's some restrictions built into this, right? Because in the way that we've set this up, is it possible for a power series to be defined with a complex center? The answer is no, right? But what the extension theorem says, it gives us the starting point for complex analysis. Because what it says is, if you start with a real power series, which by necessity is expanded around a real number, then that power series can be thought of as a complex power series with the same center. But this is only certain, I mean, there's a huge family of functions we can't get by doing this, right? Anything purely complex is not going to be able to be attained this way. And any radius, any sort of set of convergence that doesn't have a center sitting on the real axis is also not possible to attain this way. So this is just the beginning of how we would like to develop complex function theory. But it gives us a place to start because it gives us access to some really important ideas. I'll point out that the theorem that we really want here, where eventually we're going to get to, is something called Taylor's theorem. So Taylor's theorem for real variables tells you how to find a power series. Does anybody remember what it is, actually? So I give you an infinitely differentiable function, and I give you a point, and I say, find the power series of the function. How do you do it? F of x is equal to the nth derivative of f evaluated at the point A divided by n factorial times x minus a to the n. So the point is that what this does is it gives you a construction of the power series, right? Taylor series for real variables gives you a construction of the power series. It gives you a way, if you have an arbitrary function and that function is infinitely differentiable, then you can apply the Taylor's theorem to get what the series must be. It gets you more than that, actually, because it also tells you what the remainder is, like how close your approximation is. So there's a whole part of Taylor's theorem that basically nobody learns, which says how good the approximation is, which we'll talk about when we get there. But the idea is that what comes out at the other side of this is a function that has derivatives that perfectly match the original. Yep?
You're talking about convergence and convergence on the real numbers. Is it always purely circular radius of convergence? Is it possible to have
yes, actually, so that's an excellent question. So let's talk about like domains of convergence. What I want to do is so I'll give you a plan for the day, right? For the day, what we're going to do is we're going to take the extension theorem and we're going to use it to develop what e to the ix actually is and how trigonometry sneaks into complex analysis. So the plan is to get the polar decomposition today of complex numbers, which is much more concrete, and then to do some examples of polar decompositions and the calculation of radius of convergence. But prior to that, let's actually talk about, when we talk about series converging, let me give you an idea of like what that actually looks like in practice. So the question is it always a disk? And the answer is yes. For a particular representation, it's always a disk. And then there's a question maybe you've not thought about before, which is, well, is that the best you can do, or can you go outside of the disk? So let's talk about radius of convergence. Okay, I have that in the book. I can see it. Nice, you guys all took pictures anyway, and I'm recording myself. Okay, so it's a theorem actually. So this is part of the root test, the root and ratio test. Basically says that if you have a series that looks like this, n is equal to 0 to infinity, and you compute the limit as n goes to infinity of 1 over the nth root of the absolute value of Cn, that this number that we call r, if that limit exists, it's the radius, and it is the largest radius on which this series will converge. So this radius right here, basically what you're measuring is the distance to the closest asymptote of the function. So this r, in some sense, is the optimal r. The theorem says that this series converges for all z minus a less than r, and not only that, it diverges outside of that. And then actually for r, who cares, right? We're working with open sets, so the boundary doesn't matter for us often. essentially what's going to happen is you're going to get a boundary where oftentimes asymptotes will be distance r from the center A. So what the root test or the ratio test, this is the same limit, by the way, as if I do this. Same number either way, 1 over that. What you're doing is you're measuring the distance to the first place where the function has a hole in it, a hole in the domain, where it's undefined. Yep?
Does that mean, like, is forced to indicate that you take one of the non-realistic coefficients, but the exact same value as the limit in the limit as the ratio of this?
Yes.
That's cool.
Yeah. It's actually quite striking that you get the same result either way. Both of them are different ways of, basically what you're doing is it's two equivalent ways of measuring how fast the coefficients die off to 0. Right? The fact that they're equivalent is actually a pretty serious theorem in real calculus. Okay, so what does it mean? Well, if you had a series like this, you can actually already tell me what r is. If you had 1 over 1 minus x, say that's f of x. So just say it's a real function now. And we'll imagine that the real function is sitting on the real line, and I'm just thinking about its domain. I don't even know why I have this purple marker. All right, so I've got this domain. This is r. And I'm imagining that I'm going to plot the domain of this for which this function converges. Now, you guys already told me last time that this is equal to the sum of x to the n, and that this converges where the absolute value of x is less than 1. I believe. Everybody told me that. It's a geometric series. And so if this is 0 and this is 1, what you end up with is this band. Oh, wait, no. Wrong way, right? Centered at 0, since it's a Maclaurin series. 0, 1, where there's an asymptote in the function. And essentially what you're saying is that the domain of this thing, where it converges, from the center, the best you can do is have this thing defined until you get to an asymptote. And then it falls apart. Okay? And so when you extend that to to complex function, and you get the disk, it's generally the same thing, the same behavior as what you're picking up. You're measuring the distance from the center to the closest asymptote. And in fact, you guys may have come across examples in real calculus where the radius of convergence, where the function is defined everywhere and looks really nice, but the radius of convergence of the power series is not all of R. So the specific example, does anybody know the example I'm thinking of? So think about f of x is equal to 1 over x squared plus 1. This is a very typical function to think about in a lot of applications. Now it looks like it's defined everywhere, right? There's no real number that's going to put a 0 in the denominator here. This has no asymptotes, no real asymptotes. But what you'll find if you try to use Taylor's formula or this formula by manipulating this formula to find a power series for it, what you'll find is it has the same radius of convergence. So if you actually do Taylor's theorem and you compute the power series for this thing, what you're going to find is that r is equal to 1. And the question is why? That function is infinitely differentiable. This is an infinitely differentiable function. What's the problem?
It's only differentiable in the real space.
In reals, that's the issue. Is that what you may not have been told when you studied this function, if this even came up, when it usually gets rolled out as an example of a function that is perfectly well behaved on the entire real line, infinitely differentiable, no problems at all, no asymptotes, really smooth function, but it has a power series that only converges on a disk of radius 1. The reason is, secretly, the only power series theorem is the power series theorem in complex numbers. And when you do this, when you do the ratio or root test to figure out what the radius of convergence is, you pick up the complex roots when you do that, even if you're looking in the real case. Because where are the roots of this thing? I mean, this factors, yep.
On the axis at plus or minus I.
X plus I times x minus I. In complex number, this thing factors. And so when you do the power series for it, even though you don't see them in the real case, this actually has holes in the function at plus and minus I. And so the best your power series is, I mean, the extension theorem implies this. The best you're ever going to do is this circle. You can't get past this, because if this worked, if you could find a real power series that went past this, it would also work for the complex case as well. But that would mean that you had a power series at an asymptote. So really, secretly, calculus was also complex analysis, but they couldn't tell you, right? So this idea that even the real functions encode intrinsically this complex behavior is part of, I mean, this goes to your question about is it always a disk, and then what actually measures how big the disk is. It's explicitly distance from the center of the power series to the first or closest asymptote of the function. Will be the largest disk on which a particular power series will converge.
And can it ever converge outside that disk?
Yes, actually. So here is a trick that complex analysts like to play. And I wasn't going to introduce this yet, but now you guys have opened a can of worms. So I'm not going to prove this. I'm going to give you an idea about like why complex function theory is so useful. If you're done with real series, if you're working with real series, you're just done. That's it. You have power series, that's where it converges, and you're finished. If you're working with complex series, you can play a different game, which looks like this. You can actually do the same thing for real series as well. So imagine that we have that same function. Let's do 1 over 1 minus x. And it has an asymptote here at 1. So I have not introduced this theorem yet. But you do a power series expansion. And so this turns into x less than 1, turns into 1 over 1 minus z is the sum of z to the n whenever we're in that circle. Modulus of z is less than 1. Totally well-defined thing, centered at 0. And now you say, well, if I stay away from the only asymptote the function has, why can't I just build another power series? So just imagine for a second that we figured out a way to build a complex power series at a different center. Let's put it right here. You say, okay, well, there's the center 0. What if I do a different power series for the function? Maybe I could put a power series for the function right here. We'll try to use another color here. It won't work, but I'm going to try. Okay. What would the radius of this particular power series, say you do a power series construction with that center, what are you going to get? Where is it going to converge? Well, you go over here. That's the radius of convergence because it's distance from the center to the closest asymptote. And you draw a disk, and you end up with some shape that looks like this. And now you've got a different power series. So the same function has one power series on the black circle and a different power series on the purple circle. So the big question here should be, what about where they overlap? You have two different series for the same function. This would really only be useful if the function was the same function on the overlap. I mean, what do you think? Should it be? I mean, it would feel really bad if it wasn't, right? If you did one power series for this function here and did this totally legitimate move, I mean, we'll see that it's legitimate, where we construct a different power series with a different center, where they overlap, I mean, how could it possibly be the case that I'm looking at two functions? Where they overlap, it should be the same function. And so this is the content of a theorem called the identity theorem in complex analysis, which says that if you have a setup like this and two functions agree on any open set, all of any size, then they agree everywhere on their domains. The power series aren't the same, but the functions are the same. Yeah.
So if you put the center of that series arbitrarily far down on the complex one, could you get a radius of convergence that was the
I'll give you. I'll raise you one. This is how complex analysts actually do it. They say, I'd really like to know what this function is doing out here. So how do I do it? Well, I do this circle and then this one. And I'll do another power series right here. And then I'll do another power series right here. And I'll do another power series right here. And I'll do another one right here until I finally get to the point where my center contains the point that I'm interested in. This is a really, since this overlaps this, they agree and so they're the same function. And since this overlaps with this, they agree and are the same function. And this idea that I'm waving my hands at right now is called analytic continuation. And it is one of the most powerful things you can do with complex analysis is expand in power series and then assert that they're the same function. So if they overlap anywhere, they're the same function. Did you guys ever see the number file video that argued that 1 plus 2 plus 3 is equal to minus 1/12? Okay, I did a talk at a conference one time about how wrong this was. And like what's actually going on here. The reason that this is true, if you've taken any time to look at it, is precisely for this reason. You can define a function that recovers p series called the zeta function, and then the zeta function is only defined in terms of a power series over here. So what you do is you cheat and you just define other power series going back that way, where you say, oh, well, they overlap, so they're the same function. And when you plug the number in over here, minus 1/12 is what comes out. So it's an analytic continuation argument. Complex functions can be extended basically anywhere as long as you avoid the asymptotes. Yep.
So why is it not true?
Well, because this is not really the value of the, it's not really the value of the zeta function. The zeta function is not defined for n equals 1. Right? You extend the function, and then you put the 1 in, and minus 1/12 is what comes out. Well, I mean, we'll talk more about that when we get there. Yep.
Why use like 6 instead of like 2?
You could use, well, I mean, you can. The idea of like scooting down here and drawing a really giant disk, that also works. It turns out that you can actually do this on an annulus as well, which is another thing that, so what is an annulus, by the way?
Like 2 circles.
Yeah, so where we're going to go with this eventually is that there's a center, and then if you have an asymptote right here and another asymptote, say, right here, you can actually define a power series that exists on the band between them. But it's not a power series anymore. It has negative powers of z in it. It's called a Laurent series. So, yeah, we're going to be just beating series to death in here. So yeah, like a big part of complex functions is actually studying the domains on which they're defined like this, different series to analyze their behavior. We are going to get a lot of ground out of the fact that we can say a lot about what this integral is. We haven't defined integrals yet, but we're going to get there real soon. Okay, now you guys are taking me way far afield into theory, and I don't want to talk about theory. I want to talk about concrete things right now. So we'll come back. I promise we'll come back to that. I promise. I promise. We got to do some basics. We got to do some basics first. So analytic continuation is going to be on the idea of existence of power series and overlap. You can read ahead if you want about the identity theorem. There's a lot of things we haven't shown yet. We have not shown that is there a Taylor theorem? Maybe. Is it the case that, I mean, if there was a Taylor theorem, that would be an assertion that differentiable implies analytic. Right? How do you get a Taylor series? You take derivatives of a function, and then you use the derivatives of the function to build the series. So the Taylor theorem would tell us that if we had a function that was differentiable, then it would have a power series. That would be a proof that holomorphic, which remember means once differentiable, which implies infinitely differentiable. This would mean holomorphic would apply analytic. The existence of derivatives would imply the existence of a power series. In the other direction, I spared you guys the really gnarly proof that once differentiable implies infinitely differentiable, but that's coming. Yep.
Like, doesn't the existence of a power series not necessarily guarantee that it actually converges to the function?
That's guaranteed by the root test. It's part of the Taylor theorem. Part of the Taylor theorem is that it uses the root test, and the root test asserts that the radius of convergence guarantees you that the series converges to the function. This is part of why we work on open sets, because for real theory, it's not true that we necessarily have that agreement, but we're forcing it by definitions here. Yep. Oh, it's all right. Okay, so let's get like some practical stuff for a second here. So we showed that e to the ix, given that e to the ix is just an extension of the series e to the x, I'm allowed to put i's into it. And so last time we showed that this was true. As long as we're willing to argue that cosine of x. Remember, there's this nothing but real theory here. Minus 1 to the n over 2n factorial x to the 2n. Sine of x is the sum of minus 1 to the n, 2n plus 1 factorial x to the 2n plus 1. Okay. So cosine x plus I sine x, if I start plotting that on the complex plane, so the real part of z and the imaginary part of z, and I plot points where the real coordinate is a cosine and the imaginary part is the sine, does that look familiar? I could think of an object that you've studied basically for your entire mathematical lives, where their points have coordinates cosine x, sine x, which is called the unit circle, which is back again. So it turns out to be the case that if you think about the coordinates of e to the ix as cosines and sines, this is e to the ix, that means that e to the ix represents every individual e to the ix represents a point on the unit circle. And that means that we're going to be able to use all the polar decompositions that you got from polar equations and parametric equations, but translated to complex analysis. And in fact, this is a very, very useful thing to do. Yeah, so normally, to emphasize the fact, I mean, so what role does the x play here? If the cosine x and the sine x have the x inside, where is the natural place for the x to go in this picture? Well, it's an angle. Okay. So maybe I should write e to the I theta to really emphasize the fact that we're talking about angles in the unit circle. So e to the I theta is cosine theta plus I times the sine of theta. Okay, and theta has a special name, complex analysis. It's called an argument.
Is the argument always theta, or are there other things that are also arguments?
I'm using theta to emphasize the fact that, like, when we see e to the I anything, we think of the anything as an angle, right? That's really, because we're doing this translation here, where we're thinking about the sort of the old trigonometric right triangle. And the full picture of the trig right triangle is this. So let's draw the whole thing. If you had this point out here was cosine x, sine x, and this point right here was theta, how far would that side be? Cosine x. Well, it's just the unit circle version is like this, right? That's the unit circle version of the picture. Radius 1, cosine x, sine x. Yeah, I think. Looks. I mean, I don't know why I'm using x here. Sorry, cosine theta. So what if I have something? Okay. What's e to the I pi over 2? Because you guys all, of course, at this point in your lives, remember your unit circle. Pi over 2 has coordinates 0, 1 in R2, but in complex analysis land, that means 0 plus 1i. So all you're doing here is recovering the old unit circle coordinates. Which means I could do all kinds of things to it. What's e to the minus pi over 4i? Don't worry, I've given you some homework to practice this. Okay, so let's see. Minus pi over 4 means I go this way. So the coordinate, it's pi over 4. So this must be minus, no, positive root 2, minus root 2. Okay, so this is root 2 over 2 minus I root 2 over 2. Oh, but it's so important to this. Oh, this is going to get so much worse. Okay, so first thing we can do here is we can extend this idea to numbers that are not on the unit circle, right? You have polar decompositions for Euclidean, actually, what are the polar decompositions for Euclidean numbers? You have x, y, and you want to convert it to r theta. What are the equations you use? Don't sigh at me. R. I start with x and y, and I really like to know r. How do I find it?
R is square root of x squared plus y squared. And it's, theta is inverse tangent.
And theta is,
Inverse
I'll make it
tangent.
easy on you. The tangent of theta is equal to y over x, right? These are the equations that you use to translate from two variable Euclidean coordinates to two variable polar coordinates, right? This is the polar to Cartesian change. The same rules work in complex analysis because you can imagine that if you had some z which was equal to a plus ib, and so you think of the coordinates of the point as ab, you can draw exactly the same picture. There's an a on this side, there's a b here, so this side is the square root of a squared plus b squared. And the angle here, I mean, imagining that that's a big fat dot that everything beats out of here. The theta that's right here is still governed by this b over a relationship. Tangent of theta is equal to b over a. So every complex number has what's called a polar representation, where the radius is just the length. Notice this is the modulus of z, right? This is the length of the complex number. And the theta here, you get by doing this tangent argument. And what that means is that every z, this is all induced by this identity, every z, every complex number z can be written z is equal to r e to the I theta. This is called the polar form. Now, there were a lot of people that yelled at me last time about solving a quadratic equation with complex numbers in it, because it kind of sucked. But what would happen if instead I had this? What if I had z squared is equal to r e to the I theta? How many answers do you expect this equation to have? Two. Okay. So if you actually sort of just naively took a square root here, and you think, okay, so z, I don't know how to deal with the plus or minus thing at the moment, but maybe we can just do this, root r, and then e to the I theta to the 1/2, so power to a power, that would mean e to the I theta over 2. That should solve the equation. Because if you squared that, what would come out? Well, squaring it would kill the square root on the r. And squaring e to the I, this works exactly like the exponentials that we know and love, right? If you square this, the 2 goes inside and multiplies the theta over 2. If you took root r, e to the I theta over 2, and you square it, you get the square root of r squared times e to the I theta over 2 squared, which is r e to the I theta. So that's at least one of the answers to the equation. Notice that's way easier than the a plus ib thing I was having you guys do last time, right? There's a couple of issues here that need to be addressed. The first is, that's only one of the solutions. So we're going to have to talk about square roots and the way that nth roots work in complex numbers. The other issue is actually related to the argument itself. So what about the big question that we're going to drive toward answering is, what happens, where does the other root come from? There must be another root. Damn. But what's actually going on here? So you imagine, let's just imagine that we're on the unit circle for a second, right? So radius 1. And I just tell you that I know that z squared is equal to e to the I pi over 2. E to the I pi, let's make them better. E to the I, yeah, that's fine, pi over 2. So Right there. How do I know it's right there? Because it just says turn pi over 2 radians from the real axis. Oh yeah, there's no degrees in here. Only radians. There's no degrees anywhere. Degrees are terrible. Forget they exist. Pi over 2. E to the I pi over 2 is representation of pi over 2 radians on the unit circle. How would I take a number and square it and get e to the I pi over 2? What's an angle that would do that? If I multiplied the angle by 2, I would land at pi over 2. Okay, let's check. E to the I pi over 4 squared is e to the I pi over 4 times 2, which is e to the I pi over 2. Ah, cool. So one of the answers to this equation is right here. Because if you double that angle, you get that one. Is there another one?
Yeah, you could, the other way, rotate clockwise.
Rotate clockwise.
Negative 3 pi over 2.
Yeah.
Oh, let's see. So what you want to do is to go all, like around to negative 3 pi over 2. So you want to be over 3 pi over 4.
Yeah.
So you're looking to be over here.
Yeah.
E to the minus I 3 pi over 4. I'm trying to jostle some trig memories here. What happens when we do that? We take e to the I 3 pi over 4 minus, and we square it, and we get e to the minus e 3 pi over 2, which says go 3 pi over 2 radians backwards. Positive angles go this way, negative angles go this way. So this angle is measured like this. And if I do that twice, guess the idea is that we end up back where we started. Minus 1 pi over 2, minus 2 pi over 2, minus e to the minus I 3 pi over 2. Oh, cool. Those are the two answers to the equation. Yep.
If you have a negative R value, that means your R.
We never take negative R values. That is a convention of complex analysis, is that we will never deal with negative radii. Any ambiguity is going to be, this is the next point I'm going to make, all the ambiguity in complex analysis is in the argument of the number, not the radius. So we will always take positive square roots of real numbers when we're dealing with this. Okay? Okay, so now we have the weirdness of the situation that z squared is equal to e to the I pi over 2 has the answers z is equal to e to the I pi over 4 and e to the minus I 3 pi over 4.
Well, isn't it also periodic though? So can I do e to the, like e to the, I guess, I can't do this. I even
9 pi over
sorry,
4.
or the other one, yeah.
And e to the, they subtract 8 from that and you get e to the minus I 11 pi over 4. And then you can keep going forever.
Yeah.
So here is the issue with using the argument as a way to talk about this. How many solutions do we want this equation to have?
2.
Just 2. I want quadratic equations to have 2 solutions. So when I'm setting up the polar representation of a complex number, I have to pick a domain for where the angles live. I have to choose a domain for these functions. I insist that numbers have unique representations. What good does it do to do function theory where numbers are not uniquely represented? Right? This is basically saying there's more than one way to show the same number. That's an ambiguity that shows up when you study trig. We don't want that here. We want there to be one way to show every number. I mean, on the unit circle, these are the same number because you go around the circle again and you get back where you started. I don't want that if I'm studying things in calculus. So because complex analysis is so heavily dependent on the idea of argument, we're going to have to be really careful about what we allow arguments to be. So if we don't make a choice, so the problem here, is that every complex number has infinite representations. because on the unit circle, theta is equal to theta plus 2 pi k, right? The unit circle points repeat their representation. Cosine of theta is equal to the cosine of theta plus 2 pi k, and so is sine. There's periodicity we need to deal with. So what we do is we restrict the allowable arguments. So I'm going to make the following assertion. The principal value of the argument is strictly between minus pi and up to pi inclusive. So we're defining the allowable arguments to run from here to here, from minus pi to pi. Those are the allowable arguments for the principal part of the argument. The inclusive side is the positive pi side, not the negative pi. So we're starting from negative pi but never picking up negative pi, and we allow ourselves to come up with angles that wrap, sorry, that's nonsensical, from minus pi all the way around to pi. Now let's, yep.
Why not negative 2 pi?
It actually has to do with, you can actually make that choice. I mean, the real issue here is that we want these things to line up with the way that the trig, inverse trig functions are defined, and it's easier to do it symmetrically around the origin than to try to do it asymmetrically. So the one thing to keep in mind about why use symmetry here is that complex analysis was invented in part to study things like diffusion of heat along a metal rod, and it was much more natural to put the 0 in the middle and see how things distributed evenly. Plus, like when you're doing symmetric functions around the origin, you can do all kinds of tricks with integrals. Okay, so there's this weird function that only shows up in complex analysis, which is called capital arg z. Capital arg z is the principal argument of z. And it's equal to the theta if z is equal to re to the I theta or minus pi less than theta less than or equal to pi. Once I make that restriction, every point has a unique representation. Now you might say, well, it's arbitrary. Why not use different angle ranges? And the answer is I could. I could choose any range of 2 pi radians I wanted. So let's think about this argument function for a second, because it's got some issues. One major issue here. First off, is this defined at 0? The way they get around this in your calculus book is they tell you, oh, write pole at 0. So this is not actually a defined function at 0. 0 has no argument. You have to make choices about that. The second thing is, how does this thing behave? This is going to be a weird move here, but I want you to think about this as a function. It has an input, z, and has an output, which is an angle. So I want you to imagine that you restrict yourself to some circle. Let's just draw a circle of radius 2, say. Oh, yeah, that's great. So there's a circle of radius 2. That's a circle r is equal to 2. Let's imagine what happens to the argument of z as we travel around this circle. What is the argument of z right here? 0. What's the argument of z right here? Arg z is equal to pi over 2. What's the argument of z right here? Okay, so arg z here is pi. As I come along this circle towards the origin, the value of the argument of z is pi. Right? What if you go the other way? Well, let's see. What if you're right here? What's your argument? Arg z is minus pi over 4. Wow, you guys are making a big assumption about that line I drew right there. Okay, what if I'm right here? See how tattooed into your brains the unit circle is? Minus 3 pi over 4. What is the value of the argument as I approach this line from this side? Oh shit, it's not continuous. It's not a continuous function. The core function of complex analysis is not continuous. The argument of z, as I sneak into this line from the bottom, argument of z is minus pi, or I should say close to minus pi. The limit is minus pi, right? You come in this way, those arguments are negative, 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 which means intrinsically, we're not allowed to consider functions that go across this line if we're going to use arguments. Every complex function that we pull apart this way has this barrier inside of it. Because if we're going to use argument to describe what's happening, we have a discontinuity that happens right here. We leap from pi to minus pi if we go this way, when really what we want to happen is that we continue on to the next larger negative value. So this barrier right here, where we have the discontinuity in the argument, this has a fancy name too. Anybody know the fancy name for this? This is called a branch cut. And this is going to be the beginning of what we'll talk about next time is this induces all kinds of problems in the analysis of functions. In fact, this makes inverses very hard to deal with, right, and weird. So we're going to talk about the effect that this has on finding inverses, which is sort of like the big topic of next time is inverses. And we're going to talk about what are called Riemann surfaces, which is a way of showing how domains stitch together so we can we sort of cheat and remove the branch cut by coming up with a way of doing two domains. Like you wrap around the circle twice, but somehow you think of them as being independent from each other. That's annoying. I should point out that generally, once you've selected an argument function, so you can choose in this book, in this class, the way that we define argz with a small a is equal to theta, where z is equal to re to the I theta, and theta falls between the range from, I believe, minus pi plus some 2 pi k up to pi plus that same 2 pi k. So some rotation of the plane. There's an infinite number of argument functions based on which values you've chosen to work on for angles. And really, as long as this range is 2 pi long, it doesn't even matter if k is an integer. You can rotate it wherever you want. That's the first thing. Okay, so what is the argument of root 3 plus I? All I'm doing is I'm tricking you by taking a problem that's really just a trig problem, right? Yeah? Okay, well let's see. Root 3 plus I, that's going to be something like the tangent of theta is equal to y over x. And then you have to go deep in your well of unit circle knowledge to realize that that happens when, if this had been 1/2 and this had been root 3 over 2, that hasn't changed the problem, which means the y-coordinate was 1/2 and the x-coordinate was root 3 over 2, so this has got to be pi over 6. This is the sort of thing that I give you a couple exercises to practice on, because it's important to be able to think about the translation of these numbers into these numbers. Would it be correct? What if I did this? I'm going to give you a different one. What is the argument of root 3 over 2 minus I 1/2?
It's minus pi.
Is it minus pi over 6 or is it 11 pi over 6? Why? Okay, capital A means that we're strictly between minus pi and pi, which means that this must be minus pi over 6. I know this is obnoxious. It probably brings back bad memories of inverse trig functions and the restrictions on the domains of those things, but it is very important, as low level as this seems compared to the power series stuff that we were doing. Accurately identifying the argument of complex numbers is really important. Okay? And the last thing I'm going to leave you with today is I'm going to give you something to think about. What do the solutions to this equation look like on the unit circle? Z squared is equal to 1. What are they? 1 and minus 1. Okay, what do the solutions to this equation look like? One right here, because that doesn't move. Then if you had 2 pi over 3, and you cubed it, the 3's would disappear, and you get e to the 2 pi I, right? So 2 pi over 3 should be 1. Well, where's the other one? Where are these? Okay, so here's your challenge. Find a formula to describe these things. Solve z to the n is equal to 1 for me. Describe all solutions of root z of the z to the n is equal to 1. These are central objects called roots of unity. Because in complex numbers, every polynomial has the number of solutions that are equal to the degree of the polynomial. Okay? So my challenge to you, without reading the book, is to come up with a formula for this, guys. Be good for you. And make sure that the arguments that you use are the arguments that fall in the principal branch of the argument when you do it. All right, so next time we will talk about inverses and Riemann surfaces. We'll talk about solutions to polynomial equations. And we'll get started on some complex geometry. So thanks for putting up with the basics here. I will keep trying to mix theory and the easy stuff together.